All right, good night, everybody. Tonight we're going to talk about two more types of chemical reactions. We've just finished an in-depth study of precipitation reactions, which are a type of double displacement reaction. Tonight we're going to finish our double displacement reactions by taking a look at acid-base reactions, and then we're going to start an investigation of oxidation-reduction reactions. So acid-base reactions are our second double displacement reaction that we're going to look at. Acid-base reactions are reactions in which an acid and a base react to produce water and an aqueous salt. You know you have an acid-base reaction when you see an acid as a reactant and water and some sort of aqueous ionic compound as the two products. Before we get into our basic equation and our specific example, I want to take a minute and define the difference between an acid and a base. Acids are substances that produce hydronium ions or hydrogen ions, otherwise known as protons. These always occur in water. An acid can have a sour taste. Blue litmus paper turns red. Acids react with some metals to produce hydrogen gas, and they also dissolve carbonate salts that release carbon dioxide. You can imagine, go back to station 3, by the way, with our Alka-Seltzer. Our Alka-Seltzer had a carbonate in it, and they produced the gas, which was a carbon dioxide gas inside the water bottle. Bases, on the other hand, are substances that produce hydroxide ions in water. Bases have a bitter taste to them. They turn red litmus paper blue, and they feel slippery to the touch. True soaps, not our liquid soaps, but a true bar of soap like Ivory or Dial, those are real soaps and they are bases, which is why they have a picture of a bar of soap. All right, let's take a look at our basic equation here. We have some acid HA, and it reacts with some base BOH. Well, just like the double displacement reactions that we learned about last week, our outer ions hook up, so HOH produces water, right? We also know HOH as H2O, and when you write out your problems, please feel free to write H2O. For right now and for your notes, I just want you to see that HOH come together, but we would write it as H2O. And in addition to that, we have B and A hooking up to form compound BA. So let's take a look at a real example here. We have hydrochloric acid reacting with sodium hydroxide. So our hydroxide and our hydrogen ions are going to hook up, right, to form water. And our sodium and chloride ions are going to hook up, our inner ions, to form sodium chloride. You do have to remember to balance your equation once you're done, but this is how you predict the products of an acid-base reaction. We're going to spend quite some time on oxidation-reduction reactions because there are so many different types of redox reactions. Tomorrow's lecture will all be about redox reactions and the different types that are involved. A redox reaction is a reaction that involves the transfer of electrons. Usually this occurs between a metal and a nonmetal. An electron transfer can happen with two nonmetals, and you usually know that this is occurring because oxygen is either a reactant or a product. These pictures I like because it kind of shows us who is who here. If we have element A reacting with element B, element A has some ions on it. It's got extra electrons. It's called the reducing agent because it loses its electrons. And actually, while it is the reducing agent, when it loses its electrons, it becomes oxidized. And element B is what we call the oxidizing agent. He gets reduced when he accepts the electrons through the reaction. I'm going to show you this on the next slide, but this is a nice little synopsis of what is happening. One thing to keep in mind, let's see if I can get that straight, guys. Maybe not. Let's take a look at this guy. I've got this lion, and if we keep our a little saying here, Leo says grr. Leo the lion says grr. When whoever is losing electrons gets oxidized and whoever gains electrons gets reduced. We're going to take a look at that in the next slide. Write down Leo says grr. We're going to spend tomorrow night's lecture all about redox reactions, but I at least want to give you one example tonight so you can kind of understand what's happening when we talk about an electron transfer. Take a look at this picture below. Here we have some copper metal being placed into a solution of silver nitrate, so AgNO3, and that's aqueous, right guys? And take a look at what's happening here. You see that white silvery metal being formed in that coil? That's silver metal. It's literally getting kicked out of solution. So let's take a look at how we would write that as an equation. We'll start with copper metal, and that's a solid, and we react it with silver nitrate, which was aqueous. We can physically see that silver getting kicked out of solution. So what happens is copper comes in and knocks silver out of its bond with nitrate. So silver has nothing else that it can do but precipitate out. Oops, excuse me guys. We want a plus sign there, not an arrow. So plus copper nitrate, but this is copper 2 nitrate. And that's aqueous. We have to balance this guy. Because there are 2 nitrates in copper 2 nitrate, we have to make sure we have 2 nitrates on the reactant side. That gives us 2 silvers, so we have to put a 2 in front of our silver. What's happening though at the atomic level here? I'm going to just kind of shrink this down a little bit. Let's see if I can shrink this down a little bit too. I need some more room, sorry. Alright, let's draw some pictures. So we've got an atom of copper, right? 1 atom according to our picture. So here's an atom of copper. And it's being mixed with 2 silver nitrate formula units. So we've got an Ag plus and an Ag plus, and it's hooked up with a nitrate. So let's hook that up with a nitrate. NO3 minus, NO3 minus. What happens here is that the copper loses electrons. So here's your Leo. Copper donates 1 electron to the silver here and 1 electron to the silver here. So copper is Leo. He loses electrons, he's being oxidized. So let's make sure, let's write that down. Okay. Copper, well, let's see if I can get a different color for us. Okay. Copper is oxidized because he's Leo. Okay. Now the silver ions are being reduced because they gained electrons. They say grr. Gain electrons get reduced. Leo says grr. So silver gets reduced, copper is being oxidized. What does that look like when we're done, right? That's the question we're wondering. So we have 2 silver atoms that are just plain old Ag, nice and reduced, no ions of any kind. And then we have a copper ion, copper plus 2, who is now bonded with 2 nitrates. Everybody's happy, the charges are balanced, but what I want you to understand here is that there was an electron transfer. Copper basically kind of paid off silver to butt out of its relationship with nitrate so that copper could hook up with the nitrate. We call this redox reaction. This particular example of a redox reaction is also known as, let's see if I can get a cool color, here we go, a single displacement reaction. And we'll take a look at that a little bit more tomorrow, because what we need to learn about is that the single element, such as copper up here, needs to be more active than silver in order to be able to displace it. In this case, copper does knock it out. You can see it in the picture. And it does so by donating electrons. It loses electrons, so it gets oxidized. Silver accepts those electrons, getting reduced. So Leo says Gur.